In this video, we take a look at changes of state, the sublimation process, applications of it, and phase diagrams. So sublimation is when a substance goes directly from the solid state to the vapor state. It doesn't become a liquid. As it changes, it goes directly to it. This occurs for substances whose vapor pressure already exceeds the atmospheric pressure, so therefore, if it were a liquid, it would be boiling already, and therefore goes directly to a vapor. You see this most commonly with dry ice, frozen carbon dioxide. Since carbon dioxide at room temperature is already a gas, and as you cool it down, the vapor pressure still exceeds that of the atmospheric pressure and would go directly to a solid. And conversely, when that solid warms up, it is already going to be at a boiling state, so therefore it goes directly to a vapor. So that opposite process when you're cooling it down and it goes to a solid is called desublimation or deposition. So sublimation has some very practical uses, especially with food that we use very commonly every day. So one way in which we use sublimation as an advantageous process is in food storage. We ship food really long distances, then we want to keep that food from going spoiled or going rotten, and we want to keep it cold to prevent bacteria from being able to rotten that food. And so we use dry ice, frozen carbon dioxide, because it sublimates. Not only is it really cold, but it also doesn't turn into a liquid state and then cause a wet, soggy mess like you would have with regular ice. It turns into a gas, so you don't have boxes of food or food itself sitting in a puddle of water. Also, freeze drying is another process in which you take your food, you get it cold, you freeze it on down, and then you lower the pressure around to cause the water within it to sublimate, removing the water out of that food to then prevent it from going rotten also, because bacteria like to live in a watery, wet environment. So if you don't have a wet, watery environment, your food can't spoil. So you see it here with this astronaut ice cream. Also, like in coffee, it's a very common process. Another common use is in purification, so taking a solution and trying to get back out just one singular substance from that solution. Just like distillation, we use it sublimation and purification by doing the same thing, kind of like freeze drying, of taking that solution and either freezing it if it's not already have solid in it, and then lowering the pressure again to have the substance we do not want to sublimate off, leaving behind the pure substance that we do want. And lastly, with air fresheners, very commonly you see with this kind of air freshener here, when you unscrew the top, allowing air to get at it, it will sublimate, and over time it'll release those fragrances, reducing odors, and it also you see it kind of wane away at time, and eventually nothing left. So for every substance, they have what we call a phase diagram. It relates temperature and pressure for any given substance, and it shows where, under those sets of conditions, where it's a liquid, it's a solid, it's a gas, and also between those phases, where they are in equilibrium. So when you have these different regions of the graph and they're separated by this line between, say, a solid and a liquid, then between that solid and liquid, the line separating them, then solid and liquid are going to be in an equilibrium. So freezing and melting would be going on at the same rate. Same thing between a liquid and a gas. Between a liquid and a gas, you'd have boiling or vaporization with condensation happening at the same rate. So there's some significant points that are labeled on a phase diagram, one of which is the normal melting point, the temperature at which a substance will melt or freeze, for that matter, at 1 atmosphere pressure, 101.3 kPa, or 760 millimeters of mercury, whichever you are looking at in terms of the standard pressure. It also has the normal boiling point, same thing. At what temperature does a substance boil when it's at that standard pressure, that 1 atmosphere of pressure? And then you also can again see those melting, boiling, sublimation lines, those lines that separate those different phases between each other on that graph. And lastly, each substance has what we call a triple point. All those three lines actually meet at one point, and there is one point for any given substance where all three phases exist in equilibrium, and all 6 transformations between those phases also are going on in equilibrium. So you have melting and freezing and boiling and condensation and sublimation and deposition all happening at the same rate, keeping a relationship between those 3 phases at an equilibrium. It's a dynamic equilibrium because all those things are still changing, but the ratio remains constant. So here we see a phase diagram for water. Again, where we live right there at 101.3 kPa standard pressure, we see that water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. But if we were to increase the pressure, then we see the boiling point goes up and actually the melting point goes down. And conversely, therefore, as pressure reduces, that you see them get closer and closer together, the freezing point increases and the boiling point decreases, and eventually you get to that point there down below, that triple point, where at 0.61 pressure kPa and 0.016 degrees Celsius, it's actually the triple point of water. You would have water vapor, liquid water, and ice all existing in equilibrium together. Now this isn't to scale very well because obviously 0.016 would be pretty much on top of that zero, as would 0.61. That part of the graph is kind of distorted to get a better view of what's going on. But again, you could find any set of pressure and temperature and find out what state water would be in for this given given sets of conditions. Also, you could determine for that set of conditions, for let's say pressure, if you're trying to get water to vaporize, what would its boiling point be? Or if you had, at what temperature, how much lower would I have to get the pressure in order to get it, say, to sublimate if I'm trying to freeze dry?